Welcome to Sleepy Stories, where knowledge and rest share the same quiet rhythm. This is a place to learn gently, to let understanding arrive without hurry, and to rest while your mind explores. If sleep does not come right away, that is perfectly fine. The steady logic of science has its own calm tempo. You can simply listen and drift. If these moments help you find ease, you can support us with a like or a subscription so that we can continue creating nights of calm discovery. Tonight's story is about the moon, how it formed, what forces shaped it, and why its presence still influences every tide and season on Earth. To understand its origin, we begin 4.5 billion years ago, when the solar system was still a disk of gas and dust spinning around a new sun. Gravity, the simplest and most persistent law of nature, organized this chaos. As the disk rotated, it flattened. Within it, microscopic particles collided and fused, forming clusters of silicate and metal. Each collision turned motion into heat. Every new fragment carried energy forward, and gradually the fine dust became the raw material for planets. Close to the sun, temperatures were so high that only metals and rocky minerals could survive. Farther out, where sunlight weakened, water and other volatile compounds condensed into ice. These gradients determined the chemistry of every planet that would follow. In the region now occupied by Earth, the balance of heat and density favored silicates, iron, and nickel, the ingredients of a terrestrial world. Over millions of years, small bodies called planetesimals collided and merged. Their gravitational attraction increased with every gain in mass, drawing in more fragments and accelerating growth. This process is known as accretion, and it explains how scattered dust can form entire planets. The collisions were frequent and violent. Each released enough energy to melt rock and keep young worlds in a molten state. Among these growing bodies was the proto-Earth, a sphere of liquid magma turning rapidly on its axis. Its surface boiled, its atmosphere was thick with vapor and gas, and its internal heat came from both radioactive decay and the relentless impact of debris. At that stage, the solar system was crowded. Hundreds of planetary embryos orbited the sun on unstable paths. One of them, roughly the size of Mars, shared nearly the same orbit as the proto-Earth. Small gravitational tugs gradually altered their trajectories until a collision became inevitable. When they finally met, the energy released was equivalent to billions of modern nuclear explosions. The event, now called the Giant Impact, vaporized much of both worlds' outer layers and flung molten rock into orbit. For a short time, Earth was surrounded by a glowing ring of silicate vapor and liquid droplets. Temperatures in this disk exceeded several thousand degrees Celsius. Within weeks to months, the material began to cool and condense. Particles collided and stuck together, forming clumps that grew under gravity into a single body, the early moon. Computer simulations show that the process likely completed within a few years, a brief moment in cosmic time. The moon's formation did more than create a companion. It changed Earth's rotation, slowing its spin and tilting its axis slightly. This new balance stabilized the planet's climate and lengthened the day. The gravitational relationship between Earth and Moon became a dynamic system. The planet's tides pulled on the satellite, while the satellite's gravity raised bulges in Earth's oceans and crust. Energy lost from this constant tugging continues to push the Moon slowly outward, about 4 centimeters each year, an effect measured precisely with laser reflectors left by later astronauts. When the debris cooled and settled, the newborn moon glowed faintly above a still molten Earth. Its surface was a sea of magma, slowly crystallizing into lighter minerals that floated to form a crust. Heavy elements sank toward the center, creating a small iron core. Over millions of years, impacts from asteroids and comets scarred its surface, leaving craters that remain visible today because there is no atmosphere or weather to erase them. All of this began with the simplest rule of physics: mass attracts mass. That single principle shaped dust into stones, stones into worlds, and worlds into companions. The same gravity that formed the moon now keeps your body anchored gently to Earth's surface as you breathe. It is the universal constant, linking every atom to every other. When you rest, you are participating in the same law that once organized the solar system. If your thoughts begin to quiet, you can let them. The formation of the moon is not just a story of violence, but of equilibrium, the universe finding order after chaos. From the perspective of science, this balance is measurable. Angular momentum, density, temperature, and orbital mechanics all fit together like parts of a clock. From the perspective of rest, it is reassurance. Even the most turbulent beginnings can lead to stable orbits. Now that the outline of creation is clear, the next step is to look more closely at that first cloud, the solar nebula itself, and understand the physical conditions that made planet building possible. For now, allow your breathing to match the quiet pull of gravity, steady and unforced. The moon's story has only begun, but already its rhythm is familiar, a slow turning toward calm. Before there was Earth or moon, there was only the sun, newly formed, shining within a rotating cloud of leftover gas and dust. Astronomers call this the solar nebula. It stretched for billions of kilometers, made mostly of hydrogen and helium with small amounts of oxygen, silicon, iron, and carbon. The sun's gravity held it together, while its heat and radiation constantly pushed outward. Between these two forces, matter began to organize itself. In this disk, temperature and pressure changed with distance from the sun. Close to the center, where sunlight was intense, only metals and refractory minerals could remain solid. Farther out, it was cool enough for water, methane, and ammonia to freeze into ice. This temperature gradient divided the nebula into chemical zones. What later became Mercury, Venus, Earth, and Mars formed from the rocky materials near the sun, while the outer planets collected gas and ice beyond what scientists call the snow line. Within the disk, microscopic dust grains moved in slow spirals, colliding, sticking, and sometimes shattering apart again. Electrostatic forces, tiny charges that make hair cling to a comb, helped these particles cling long enough for gravity to take over. Clusters of dust grew into pebble-sized aggregates, then into kilometer-scale bodies called planetesimals. Every collision converted motion into heat. Local temperatures fluctuated by hundreds of degrees, melting and resolidifying minerals. These early processes established the chemical fingerprints later found in meteorites, providing direct evidence of how the solar system condensed from vapor to rock. The nebula was not uniform. Regions of higher density acted like small whirlpools, concentrating material and amplifying gravity's pull. Spiral shock waves from the newborn sun's magnetic activity rippled through the disk, compressing gas and accelerating growth. Computer models show that such instabilities could gather enough matter to form planetary embryos within a few million years. In these zones, iron alloys and silicate minerals combined in proportions that would later define each planet's core and crust. In the orbital region that would one day host Earth, the total mass of solid material was only a few % of the sun's, yet that modest amount was enough. Through continued accretion, dozens of Moon to Mars-sized embryos emerged. They moved in slightly different orbits, intersecting and colliding in a chaotic ballet. Each impact redistributed angular momentum, gradually shaping the disk into a thinner, more stable plane. From the outside, if one could have watched, it would have looked like a glowing ring of dust slowly clearing gaps where planets were forming. Radiation from the sun swept the remaining gas outward, leaving behind a system dominated by solid matter. By this time, the proto-Earth had begun to take shape within one of these cleared lanes. Nearby, another large body followed a similar path. Their future collision would give birth to the moon, but for now, both existed as molten embryos orbiting within a thinning haze of particles. Scientists know this sequence not from imagination but from observation. Telescopes aimed at distant stars have captured disks in various stages of this process. Some show bright inner rims where temperatures reach thousands of degrees. Others display dark gaps, clear evidence of planets carving paths through gas and dust. Spectroscopic measurements reveal the same elements and compounds that fill our own meteorites: silicates, carbonates, and ices of water and methane. By studying these young stellar systems, researchers can test every step of the theory that explains our own origin. Even in this precision, there is quiet wonder. The same rules of physics that govern those far-off disks also governed ours. Pressure, rotation, and gravity, simple principles, built complexity from randomness. From them came worlds capable of oceans, atmospheres, and eventually, thought. When you look at the night sky, every point of light surrounded by dust is a potential replay of that story. A star forming planets, perhaps a moon orbiting one of them, perhaps even life learning to rest beneath its light. As the solar nebula thinned, its remaining dust settled toward the plane of rotation, forming the foundation of the planetary system we know today. The stage was set for collisions that would sculpt the terrestrial worlds. Out of this calm but relentless physics, the ingredients for the Earth and its moon were prepared. The next chapter of their shared history would not be gentle. It would begin with impact. From the moment dust began to cluster inside the solar nebula, gravity started a chain reaction that would last millions of years. Each tiny grain, no heavier than smoke, had mass and therefore influence. When two grains met, weak electrostatic forces held them together long enough for a third to join. With every collision, the growing clump gained momentum and pulled in still more material. This slow gathering is known as accretion, the process that built every solid object in the solar system, from meteorites to planets. At first, growth was delicate. Particles collided at speeds of only a few centimeters per second. If the impact was too violent, they shattered. If it was gentle, they stuck and formed porous aggregates resembling snowflakes of stone. Over time, these fragile clusters compacted under their own weight, becoming denser. When they reached sizes of tens of meters, gravity strengthened their attraction. They began to sweep up smaller fragments in their path, carving lanes through the nebular gas. This stage produced bodies kilometers across, planetesimals, the true seeds of worlds. Each planetesimal carried energy in two forms: its velocity and the radioactive decay of short-lived isotopes, such as aluminium-26. Both sources released heat. As the bodies grew larger, they retained that heat longer, melting internally and separating into layers of metal and rock. This early differentiation explains why even small asteroids show signs of metallic cores and rocky mantles. The same physics would later define the internal structure of Earth and Moon. The nebular disk remained a busy arena. Billions of planetesimals orbited the Sun, colliding, merging, or breaking apart. Computer simulations suggest that in the region near Earth, this chaotic dance lasted tens of millions of years. Each collision changed the participants' speed and trajectory, redistributing angular momentum throughout the system. Larger bodies acted like gravitational vacuums, drawing smaller ones inward and clearing nearby space. The process favored growth. The bigger an object became, the faster it could collect mass. Within this natural competition, a few dominant embryos emerged, each roughly the size of the Moon or Mars. Among these, one stood at the center of our story, the proto-Earth. It was already spherical, its surface molten from continuous bombardment. Lava oceans glowed across its surface, and heavy metals sank to form a dense core surrounded by a mantle of silicate rock. Volcanic gases escaped into space, forming a thin, unstable atmosphere of water vapor, carbon dioxide, and sulfur compounds. Temperatures on the surface exceeded 1,000 degrees Celsius. It was a violent, unstable environment, yet perfectly suited for growth. Nearby, another embryo followed a similar orbit. It too had undergone differentiation and possessed an iron-rich core. Astronomers later gave it the name Theia, drawn from mythology, but in reality it was simply one of many planetary seeds competing for dominance. Their orbits gradually converged, driven by the gravitational tugs of the Sun and neighboring worlds. A collision between them was not an accident but an outcome written in orbital mechanics, a final step in the process of planetary accretion. Evidence for this ancient history still reaches us. Meteorites preserve minerals that crystallized during the earliest melting of planetesimals. Their isotopic ratios match the chemistry expected from solar nebula condensation models, confirming that the same material built both Earth and Moon. In laboratory furnaces, researchers replicate these conditions, watching silicate grains fuse and separate exactly as theory predicts. Every experiment reinforces a single truth. Complexity arises from repetition. Given enough collisions, dust becomes stone, and stone becomes world. In the calm of night, that principle feels almost human. Each breath, each heartbeat, each thought is another small addition to a larger whole. The same incremental logic that built planets governs the growth of understanding itself. There is comfort in knowing that the universe does not rush. It builds by patience, not force, and finds order through steady motion. By the time the solar nebula began to fade, Earth and its companion embryos had gathered most of the available material. Gas and dust thinned, the sun's radiation swept the remaining mist outward, and collisions became less frequent but more consequential. When the final, massive impact came, the one that would fuse two worlds into one system, it was the natural conclusion of this slow arithmetic of gravity. Accretion had done its work. Now creation would turn to transformation. As the last clouds of dust thinned around the young sun, a handful of planetary embryos remained, each tracing an orbit cleared by countless collisions. Among them, one body dominated the region between Venus and Mars. This was the proto-Earth, a world still half-formed but already massive enough to control the space around it. Every fragment that crossed its path added momentum, mass, and heat. The planet was not solid. It was an ocean of molten rock turning beneath a vapor-filled sky. The physics of its growth followed simple rules. Kinetic energy from falling material was converted into thermal energy upon impact. Temperatures within the upper mantle exceeded 1,500 degrees Celsius, hot enough to melt silicates. Heavy elements such as iron and nickel sank toward the center under gravity, releasing even more energy as potential energy became heat. This differentiation created a layered planet, a metallic core, a viscous mantle, and a surface crust too unstable to last. Each new impact fractured that crust, recycling it into the interior, where it melted again. As the planet spun, its rapid rotation, perhaps once every 5 or 6 hours, generated a strong centrifugal bulge at the equator. Combined with convection inside the molten core, this rotation set up an early magnetic field. Traces of that primordial magnetism are preserved today in the oldest minerals. The field shielded the upper atmosphere from some of the sun's charged particles, but constant bombardment and high temperatures meant that most gases escaped to space. Only the heavier molecules, such as carbon dioxide and water vapor, could persist. They formed a dense, hot atmosphere where pressure at the surface may have reached hundreds of times that of modern Earth. Volcanoes dominated the landscape. They released carbon compounds, sulfur dioxide, and steam in enormous quantities. These gases thickened the atmosphere and helped retain heat through the greenhouse effect. Rain could not yet fall. Every droplet would have boiled away before reaching the ground. The surface was a continuous magma ocean, its currents carrying minerals upward and inward like slow tides of stone. From space, the planet would have glowed dull red, wrapped in a haze of volcanic gas. This was the crucible from which the later solid Earth would emerge. Within this molten environment, physical separation by density continued. Iron and nickel pooled at the center, forming the core, while lighter silicate minerals floated upward. That arrangement established the planet's long-term internal dynamics. The metallic core conducting electricity, the silicate mantle convecting heat, and both interacting to sustain a magnetic shield for billions of years. The pattern of internal layering seen in seismic data today began during this violent stage. Meanwhile, gravitational interactions among neighboring embryos perturbed their orbits. Each near encounter slightly altered Earth's trajectory, raising the possibility of eventual collision. The most significant of these wandering bodies was Theia, similar in composition but slightly smaller. Over time, orbital resonances drew the two closer, their paths converging like gears turning toward contact. The energy stored in their motion grew with every approach, preparing for an impact that would define both worlds. Scientific evidence for this early history comes from isotopes locked within Earth's oldest rocks, and from computer models that reproduce the planet's angular momentum and density distribution. Geophysicists simulate the process with equations describing viscous flow, differentiation, and energy conservation. The results align. A planet once entirely molten, gradually solidifying from the inside out, while maintaining enough internal heat to remain geologically active to this day. For the listener, there is quiet awe in this precision. A world that seems stable was once fluid. The ground beneath us is the cooled residue of ancient fire. Every continent, every mountain, every ocean basin owes its existence to these early cycles of melting and reforming. The same gravity that holds you now once pulled rivers of magma across an infant planet, shaping the surface that would later cradle life. If your mind begins to slow, you can rest in that image. Heat turning to structure, motion becoming balance. What appears chaotic often hides the order of physics underneath. The proto-Earth was not a place of peace, but it was a place where the rules of nature began to settle into harmony. From its molten heart would come a quieter world, one that, after its greatest collision, would finally find companionship in the sky. In the chaotic environment of the early solar system, every planet grew by impact, yet one collision would stand apart from all others, the event that transformed the proto-Earth and created its natural satellite. Astronomers call it the giant impact, a collision between Earth and a Mars-sized body named Theia. It was not chance, but orbital inevitability. Gravity had been drawing the two together for millions of years, their paths slowly converging until contact could no longer be avoided. Computer simulations reconstruct the moment with careful physics. When Theia struck at an oblique angle and at several kilometers per second, kinetic energy turned instantly into heat. Temperatures soared high enough to vaporize rock. The outer layers of both worlds were ripped away, forming a plume of silicate vapor and molten droplets that encircled the planet. The collision did not destroy Earth's core. Instead, it mixed Theia's mantle with Earth's, explaining why the two bodies share almost identical isotopic compositions today. This chemical fingerprint, measured in oxygen, titanium, and tungsten ratios, is among the strongest pieces of evidence for their shared origin. The impact released more energy than all later volcanic and tectonic events combined. For a short time, Earth became a glowing sphere surrounded by a disk of incandescent debris, extending tens of thousands of kilometers into space. Within this disk, gravity began its patient work again. Material clumped, collided, and merged, forming a ring of larger fragments. Over the course of months or perhaps a few years, these fragments coalesced into a single body, the early Moon. Models of disk dynamics show how this process unfolded. Fragments near Earth's surface orbited quickly, while those farther out moved more slowly. Collisions between them transferred angular momentum outward, allowing the largest clumps to grow and stabilize. As the disk cooled, silicate vapor condensed into droplets that rained back onto Earth or accreted onto the forming moon. The result was a companion body made primarily of the same material as Earth's mantle but with a lower density, since most of the metal had already sunk to Earth's core before the collision. At this stage, the moon orbited much closer than it does today, perhaps only 20,000 kilometers above Earth's surface. Its presence dominated the sky, appearing several times larger than we see it now. Gravitational tides between the two bodies were immense. They slowed Earth's rapid rotation and transferred angular momentum to the moon's orbit, causing it to drift gradually outward. This tidal evolution continues even now. Laser measurements show that the moon recedes from Earth by roughly 4 centimeters each year. Geological evidence supports the theory's predictions. Lunar rocks brought back by astronauts show a scarcity of volatile elements, exactly what one would expect from material that once existed in a high-temperature disk. Their isotopic signatures match Earth's mantle with remarkable precision, confirming that both worlds formed from the same melted mixture. No other model, capture, co-formation, or fission explains this unity as well as the giant impact. For Earth, the consequences were profound. The collision melted much of the surface, creating a global magma ocean. It reset the planet's rotation, tilted its axis to about 23 degrees, and produced the stable day-night cycle that still governs the climate. Without the moon's steady gravitational influence, Earth's tilt might have wandered chaotically, producing extreme seasonal variations incompatible with long-term life. In that sense, the moon's violent birth became the foundation for stability. To imagine this is to sense both magnitude and calm. The scale of destruction is beyond direct human experience, yet from it emerged the balance that now governs our world. Every evening, when the moon rises, it is the cooled remnant of that ancient collision, proof that order can follow from energy, that even chaos can lead to symmetry. The light that reaches your window tonight began as fire, scattered through space, and gathered again into quiet form. If your thoughts begin to settle, you can rest within that paradox. The forces that shattered two worlds also united them. In the physics of impact lies the possibility of harmony. From molten debris came the moon's pale reflection, and from the violence of creation came the rhythm of tides that will outlast us all. When the dust from the giant impact began to settle, two glowing worlds faced each other across a narrow stretch of space. Earth was still an ocean of magma, its atmosphere dense with silicate vapor and metal droplets. The newborn moon, smaller but no less incandescent, orbited nearby, its entire surface a molten sea hundreds of kilometers deep. Together they radiated more heat than all the planets of the young solar system combined. The science of this stage begins with thermal evolution. As the disk condensed into the moon, gravitational energy from accretion was converted into heat, keeping the surface liquid. Infrared radiation slowly carried that heat away into space. Calculations suggest the moon's magma ocean may have persisted for tens of millions of years before solid rock began to dominate. During this period, heavier minerals such as olivine and pyroxene sank toward the interior, while lighter plagioclase crystals floated upward, forming the first crust, an anorthosite layer that still reflects sunlight today as the bright lunar highlands. On Earth, similar cooling occurred on a grander scale. The planet's molten surface gradually solidified from the top down, creating a thin crust that floated on a still liquid mantle. Volcanoes punctured this crust, venting steam, carbon dioxide, and sulfur gases. As the upper atmosphere cooled, water vapor condensed for the first time, falling as rain that hissed into instant steam before returning upward again. Eventually, the cycle stabilized, and liquid water collected in surface basins. These first oceans formed under a dimmer sun but beneath a moon that filled much of the sky. The proximity of the moon shaped every aspect of early Earth. Tidal forces were far stronger than today, hundreds of times higher. They stretched the young planet's crust, driving friction that warmed its interior and slowed its rapid rotation. Each passing day grew slightly longer, while the moon's orbit expanded outward. Mathematical models show that this exchange of angular momentum still continues. Earth's rotation loses about 2 milliseconds per century, and the moon recedes at roughly 4 centimeters per year. The same laws that once forged chaos now regulate time itself. Without an atmosphere, the moon cooled unevenly. Meteoroids struck its surface continuously, mixing crust and mantle material and leaving craters that would never erode. These impacts excavated lighter anorthosite rocks and dark basalts, shaping the contrasting features still visible from Earth. The far side, thicker in crust, remained largely untouched by lava flows, while the near side developed the vast plains we call Maria. Each difference preserves data, crustal thickness, impact rates, and internal temperature gradients. By reading these clues, scientists reconstruct the moon's earliest geologic timeline as if it were a frozen laboratory of planetary history. The chemistry of returned lunar samples confirms this chronology. Crystals of plagioclase record slow cooling in a shallow magma ocean. Small glass beads preserve traces of volcanic outgassing that once created a brief, transient atmosphere. These findings allow researchers to refine thermal models and calculate the moon's rate of solidification. They reveal a world that began as liquid fire and became a record of equilibrium, a balance between energy lost and gravity retained. Now and then, the distance between science and feeling narrows. If you look at the moon tonight, you are seeing the same anorthosite crust that floated on that primeval sea. Its pale glow is sunlight reflected from minerals that crystallized when both Earth and Moon were still molten. The quiet light you see is the memory of that heat, cooled across billions of years. It reminds us that even the hottest beginnings find calm through time and balance. As you rest, that same principle applies. The energy of the day slowly radiates away. The mind's molten thoughts cool and solidify into quiet forms. The moon, constant in its orbit, marks that process with light steady enough to measure tides and gentle enough to invite sleep. You can let its ancient rhythm carry your own breathing, slow, cyclical, and precise, like the turning of two worlds that once shared the same fire and now share the same calm night. For centuries, the moon appeared to be an isolated world, a silver sphere moving through the heavens, separate from Earth except by gravity and light. Early theories imagined it as a captured body, perhaps formed elsewhere in the solar system and drawn in by Earth's pull. Others proposed that both worlds had formed side by side from the same nebular disk. Only in the modern age, through the analysis of lunar rocks, did science uncover the deeper truth. The moon and Earth share a single chemical signature, one that reveals their common origin in the giant impact. The discovery began with the samples returned by the Apollo missions. Geologists expected that the moon's composition would differ significantly from Earth's. If the moon had been captured from another orbit, its isotopic ratios, the relative abundances of specific atomic forms of each element, would carry a distinct fingerprint. Instead, the data showed near-perfect alignment. Oxygen isotopes, in particular, matched to within a few parts per million. The ratio of oxygen-16, oxygen-17, and oxygen-18 inches lunar rocks is identical to that in Earth's mantle. No other known body in the solar system shares that exact pattern. This finding was crucial. Isotopes act as natural tracers because their proportions vary with distance from the Sun during planetary formation. Mars, for example, has oxygen and hydrogen signatures measurably different from Earth's. The identical isotope ratios of Earth and Moon could only occur if they originated from the same mixed material. In geochemical terms, it was evidence of shared ancestry, the unmistakable residue of the giant impact that blended both bodies before they separated again. Further measurements strengthened the conclusion. Tungsten isotopes, sensitive to processes of core formation, showed that Earth and Moon both differentiated at roughly the same time. Titanium, silicon, and chromium isotopes told the same story. Even the trace elements, rare metals such as niobium and tantalum, appeared in near equal proportions. The pattern was too precise to be coincidence. It implied that the Moon was born from material ejected from Earth's outer layers, not from an unrelated body captured later. Chemical composition also explains physical differences. Because the impact stripped away much of the lighter, volatile material, the Moon contains almost no water or easily evaporated elements, such as sodium and potassium. Its density is lower, and its iron core much smaller than Earth's. This matches computer models showing that most of the metallic core of Theia and Earth remained within the merged planet, while the mantle material thrown into orbit became the Moon. In this way, the chemistry of rock became the language of history, a precise record of violent beginnings. To the human eye, these facts reveal something profound about connection. The light that reflects from the Moon tonight is sunlight bouncing off minerals once part of Earth's surface. Every grain of lunar dust carries atoms that may have circled within Earth's mantle before being cast outward by impact. In a literal sense, the Moon is part of Earth that never returned home. Its orbit is not only gravitational, it is familial, a continuing relationship between what remained and what departed. Scientists continue to refine this understanding using mass spectrometers capable of measuring isotopic ratios to extraordinary precision. New analyses of ancient lunar samples and meteorites from other planets provide context, showing just how rare such chemical alignment truly is. Each result confirms that the Earth-Moon system is unique in its symmetry, a pair of worlds sharing one origin and two destinies. For a moment, you can let that image settle in your mind. One planet becoming two, each carrying the other's memory. It is a reminder that division does not always mean separation. From shared matter came individuality, and from impact came balance. In the stillness of night, that reflection becomes quiet reassurance that even what seems distant can remain connected by invisible chemistry and the slow gravity of time. After the Moon coalesced from the debris of the giant impact, it entered a long period of internal transformation. Though it now moved as a single body, its interior remained in flux, a molten sphere where heat, gravity, and chemistry competed for equilibrium. Understanding how that fluid world became the cratered surface we see today requires the study of differentiation, the process by which dense and light materials separate under gravity. At the start, the Moon was almost entirely liquid. Temperatures inside exceeded 1500 degrees Celsius, high enough to keep silicate minerals molten. As the upper layers began to cool, crystals formed within the magma ocean. The sequence of crystallization followed the rules of mineral physics. Heavier minerals such as olivine and pyroxene sank toward the center, while lighter plagioclase feldspar floated upward. This buoyant layer accumulated to form a primitive crust, roughly 50 kilometers thick. That crust, made mostly of the pale rock anorthosite, now reflects sunlight as the bright highlands visible through any telescope. Deep inside, heavier minerals settled, concentrating iron and magnesium near the core mantle boundary. This internal layering altered the Moon's moment of inertia, changing the way it rotated and interacted tidally with Earth. Computer simulations and seismic data from later lunar missions confirm that the Moon possesses a small metallic core, about 2% of its total mass, surrounded by a partially molten zone. Although far smaller than Earth's core, it likely generated a weak magnetic field early in the Moon's history, traces of which remain locked within ancient rocks. Geochemists reconstruct this sequence by analyzing isotopic and mineral compositions of samples returned from the lunar surface. Plagioclase crystals contain characteristic ratios of calcium and aluminum that mark their slow growth in a cooling magma ocean. Other minerals show zoning patterns, gradual changes in composition from center to rim that record the direction of heat loss. When combined with computer models of convection, these data allow scientists to estimate cooling rates and solidification timescales. The results suggest that the lunar crust took tens of millions of years to form completely. During this period, impacts from asteroids and comets repeatedly punctured the thin outer shell. Some penetrated deep enough to dredge up material from the still molten mantle, creating a mixed surface of light and dark regions. These impacts also helped release trapped gases, producing brief episodes of volcanic outgassing. Although the Moon's gravity was too weak to retain a lasting atmosphere, those transient plumes left chemical signatures later detected in glass beads and rock vesicles. Every crater and fracture preserved a record of these exchanges between interior and exterior. The chemical differentiation of the Moon also influenced its long-term thermal evolution. Because the crust contained elements that resist heat transfer, it acted as an insulating blanket. Heat from radioactive decay within the mantle escaped slowly, sustaining volcanic activity for hundreds of millions of years after the surface solidified. This delayed cooling explains the later appearance of vast basalt plains, the Maria, that filled low basins on the near side. In contrast, the far side, with its thicker crust, remained largely untouched by lava flows. Even in silence, the Moon developed asymmetry, its two faces shaped by differences established during these earliest stages of separation. To scientists, this record is a kind of time capsule. Each mineral and isotope serves as evidence for processes too large to witness directly yet precise enough to measure. The Moon's differentiation illustrates a universal pattern in planetary science. Energy seeks balance, matter seeks order. The same principle operates within stars, planets, and even biological systems. It is the architecture of stability built from heat and motion. For the listener, there is calm in that idea. Out of turbulence came structure. From molten disorder came layered stillness. The light you see on the lunar surface tonight originates from that ancient anorthosite crust, a surface crystallized when the solar system was still young. To know this is to recognize continuity. The same laws that once governed molten rock now govern your quiet heartbeat and the slow rhythm of breath. Each system, large or small, finds equilibrium through time. Once the Moon's crust had solidified, it became a silent witness to one of the most violent eras in the solar system's history. Between 4 and 3.5 billion years ago, the inner planets endured a barrage of asteroids and comets. This interval, known as the Late Heavy Bombardment, reshaped the surfaces of Mercury, Venus, Earth, and Mars, but only the Moon kept a permanent record. Without air or water to erase the evidence, every collision left a scar that still catches sunlight today. The process began with impacts from bodies tens of kilometers wide. Each struck at speeds of 20 kilometers per second or more, releasing energy equal to millions of nuclear detonations. Shock waves fractured crust and mantle, melting rock and throwing ejecta across thousands of kilometers. When the molten debris cooled, it formed circular depressions surrounded by raised rims and ejecta blankets, craters, the Moon's defining feature. Smaller craters overlaid larger ones, producing a complex landscape that geologists read like layers of handwriting. By counting and dating these overlapping structures, scientists can reconstruct a chronological map of lunar history. Some impacts were so enormous that they excavated entire basins. The South Pole Aitken Basin, more than 2,000 kilometers across, remains one of the largest known impact structures in the solar system. Others, such as Imbrium, Serenitatis, and Crisium, created depressions later filled by dark basaltic lava. These features divide the lunar surface into two major terrains: the bright highlands, composed of ancient anorthosite crust, and the dark Maria, younger volcanic plains. Remote sensing instruments aboard modern orbiters measure variations in gravitational pull across these regions, revealing denser material beneath the Maria and confirming that they were once molten seas of basalt. Radiometric dating of returned samples provides absolute ages for these events. Rocks from the highlands are the oldest, typically older than 4 billion years, while basalt from the Maria dates to around 3 billion years. The distribution of ages shows a clear sequence: first widespread bombardment, then volcanic flooding, and finally long cooling. Earth, with its active tectonics and weather, lost nearly all evidence of this early bombardment. The Moon, geologically inert, preserved it perfectly. Because of that preservation, the lunar surface serves as a baseline for dating other planetary surfaces by crater counting, a cornerstone method in planetary geology. Impact physics also explains many details visible through a telescope. Central peaks inside large craters mark places where the crust rebounded after impact. Rays of bright material stretching outward are streams of pulverized rock thrown across the surface. Melt ponds at the floors of basins record moments when solid rock briefly behaved like liquid under immense pressure. Every detail speaks to mechanical laws: momentum, energy transfer, and the response of brittle materials to sudden force. To scientists, these scars are not merely damage, they are data. Each crater is a measurement of time and probability, an equation frozen into stone. By studying crater density and distribution, researchers infer the rate at which asteroids once filled the inner solar system. This knowledge extends beyond the Moon. It helps determine how often catastrophic impacts might have influenced Earth's own history, shaping its atmosphere and even its potential for life. For the quiet observer, there is a paradox in this landscape. What appears peaceful through a telescope is the residue of unimaginable violence. The smooth light of the full moon hides a surface once molten, fractured, and bombarded. Yet from that chaos came permanence. In every direction the same craters shine, unchanged for billions of years, reminders that stability often arises only after energy has found its limit. When you gaze upward, the light reaching your eyes has crossed that ancient terrain, touching the rims of Imbrium and Aitken before reflecting toward Earth, a silent message from the solar system's earliest chapters. Once the Moon's surface settled and its orbit stabilized, a new kind of relationship began, a continuous gravitational exchange between Earth and its satellite. This interaction, invisible yet measurable, has shaped the length of our days, the rhythm of tides, and the long-term stability of Earth's climate. It is a relationship of motion and balance, governed by the simple principle that every force has an equal and opposite response. From the moment the Moon formed, gravity began to act like a tether. The Moon's pull raised bulges in Earth's oceans and crust, drawing them slightly toward itself. But Earth was rotating faster than the Moon orbited, so these tidal bulges were carried a little ahead of the line connecting the two bodies. The offset created a torque, a gentle but persistent drag, that slowed Earth's rotation while transferring angular momentum to the Moon's orbit. Over billions of years, this process pushed the Moon outward and lengthened Earth's day from a few hours to the 24 we experience now. The physical details are well understood. Precise laser measurements using mirrors placed on the Moon during the Apollo missions show that it recedes by about 4 centimeters each year. This distance corresponds to a daily increase in the length of Earth's rotation of roughly 2 milliseconds per century. It seems small, but accumulated over geologic time, it represents a major shift in planetary dynamics. Fossil corals and tidal sediments on Earth confirm the trend. Ancient layers show hundreds more days per year than modern ones, proof that the planet once spun faster beneath a closer moon. The slowing of Earth's rotation also locked the Moon into a synchronous state known as tidal locking. This is why we always see the same lunar face. The Moon's rotation period gradually matched its orbital period, a configuration that minimizes tidal friction and energy loss. Computer models indicate that this balance formed within the first few tens of millions of years after the Moon's creation, and has remained remarkably stable ever since. The side we call the far side still exists, but it is never visible from Earth, an eternal consequence of gravitational synchronization. Tidal forces extend beyond oceans. They flex the solid body of Earth by about 30 centimeters each day, and they once deformed the Moon far more intensely. As the Moon's orbit expanded, the mechanical strain within its interior generated heat through friction, known as tidal heating. This additional warmth may have delayed the Moon's cooling and contributed to its early volcanic activity. Even today, the same process keeps distant moons of Jupiter and Saturn geologically active. It is a universal mechanism by which motion converts into internal energy. The Earth-Moon system also influences planetary stability on a larger scale. Without the Moon's gravitational anchor, Earth's axis would wander more chaotically under the pull of the Sun and other planets. Such instability could lead to extreme swings in climate. By maintaining a steady axial tilt of about 23 degrees, the Moon acts as a stabilizer, ensuring that seasons change predictably and life can adapt over long timescales. In this sense, the Moon is not merely a companion, but a regulator, a dynamic part of Earth's environmental system. Measurements of angular momentum and orbital energy confirm that the current configuration is nearly ideal. As the Moon continues to recede, Earth's rotation will keep slowing, but the exchange of energy will gradually diminish. Eventually, the two bodies may reach a point of mutual tidal lock, where one hemisphere of Earth always faces the Moon. That future lies billions of years ahead, but the trend reveals the enduring precision of gravitational laws. There is calmness in these numbers. Every tide that rises and falls, every steady rotation of the planet, follows equations that never rush. The same mechanism that once generated heat and motion now produces rhythm and balance. When you watch the Moon glide across the night sky, you are seeing gravity's patience, the slow choreography of two worlds finding equilibrium. It is motion turned into harmony, a dance so constant that it has guided oceans, calendars, and perhaps even the tempo of sleep. Every coast on Earth moves to a rhythm older than any heartbeat. Twice each day, the oceans rise and fall under the pull of the Moon. This motion, gentle on a beach and immense across an ocean basin, is the most visible evidence of our planet's gravitational conversation with its companion world. Tides begin with differential gravity, the fact that the Moon's pull on the near side of Earth is slightly stronger than on the far side. This difference stretches the planet into an elongated shape, producing two bulges, one facing the Moon and one opposite. As Earth rotates, any given location passes through these bulges, experiencing a cycle of high and low water. The Sun contributes as well. When the Sun, Moon, and Earth align, their forces combine to create spring tides, the highest and lowest levels of the month. When the Sun forms a right angle to the Moon, neap tides follow, smaller and more moderate. Physics describes the process precisely. The gravitational force between two bodies is proportional to their masses and inversely proportional to the square of their distance. Because distance varies across Earth's diameter, the small difference is enough to shift billions of tons of water. Friction between the moving oceans and the solid Earth converts part of this kinetic energy into heat, slowly altering both rotation and orbit. The same tidal drag that lengthens Earth's day also pushes the Moon outward, a subtle but measurable exchange of momentum. In coastal regions, local geography modifies these global effects. Narrow bays amplify tides, while deep ocean basins reduce them. Some locations, such as the Bay of Fundy in eastern Canada, reach vertical differences of more than 15 meters between low and high water. Satellite altimeters map these variations with centimeter precision, transforming centuries of observation into quantitative understanding. From orbit, the planet's surface appears to breathe, oceans swelling and relaxing under predictable gravitational pressure. Tides influence not only water but also the solid Earth. The crust flexes by about 30 centimeters every day, a phenomenon measured by precise GPS networks. This deformation affects stress along fault lines, sometimes triggering minor seismic adjustments. The atmosphere, too, responds with subtle pressure waves called atmospheric tides. Together, these oscillations create a planet in constant, quiet motion, its pulse synchronized with the moon. Biology responds to that rhythm. Many coastal organisms follow tidal clocks built into their genes. Crabs, mussels, and certain fish anticipate the return of water even in laboratory tanks far from shore. These internal timers evolved from billions of tidal cycles, linking life directly to celestial mechanics. On longer scales, tides may have guided evolution itself. Early in Earth's history, strong tidal ranges created shallow pools that alternated between wet and dry, offering ideal environments for chemical concentration and the eventual transition of life from sea to land. Ancient rocks record this story. Sedimentary layers known as tidal rhythmites show paired laminae deposited by successive tides. Counting these layers reveals how many tidal cycles occurred within a lunar month. Samples from the Devonian period indicate about 400 days per year, confirming that Earth once rotated faster and that the Moon was closer. These rock calendars provide direct evidence of the same process we measure with lasers today, an unbroken record of gravitational exchange. To scientists, tides are equations in motion, proof that physical law can produce both stability and variation. To anyone listening to waves on a quiet shore, they are time made visible. The sea does not invent its rhythm, it follows geometry written in space. When evening falls and the tide turns again, it carries more than water. It carries the weight of astronomical precision, each rise and retreat a consequence of distant alignment. The moon's light across the surface is the visual counterpart to that movement, a gentle oscillation between fullness and absence. You can rest in that certainty. The planet's pulse continues whether you watch it or not, steady as breathing, exact as mathematics, constant as the turning of the Earth itself. As the planet turns and the moon climbs, light and darkness alternate in a cycle as old as the oceans themselves. Long before humans named time, the interplay between sunlight, twilight, and moonlight guided every organism's sense of rhythm. Day and night are not simply opposites. They are signals that regulate the chemistry of life, linking biology to the mechanics of the heavens. The moon influences night in two ways, by light and by gravity. While its gravitational effect moves the seas, its reflected sunlight shapes the internal timing systems that govern behavior and rest. Scientists call this biological coordination the circadian rhythm, from the Latin circa diem, about a day. It is driven by oscillations in cellular activity that repeat roughly every 24 hours, synchronized primarily by the cycle of light and darkness. Yet the moon's phases, repeating every 29.5 days, add a subtler rhythm, known as a circulunar cycle, which many species still follow. In coral reefs, entire ecosystems respond to the moon. Certain corals release eggs and sperm simultaneously during specific lunar phases, ensuring that reproduction coincides with predictable tides and brightness. Sea turtles crawl ashore to nest during the darkest nights near the new moon, when fewer predators can see them. Even insects and birds adjust migration and feeding patterns to this extended lunar clock. These behaviors evolved not through conscious adaptation, but through selective advantage. Those who synchronized with celestial cues survived to pass on their timing. Humans also bear traces of this connection. Although artificial light now blurs natural cycles, our bodies remain tuned to changes in brightness. Light enters the eye and reaches a small cluster of neurons called the suprachiasmatic nucleus, which acts as the master clock of the brain. This cluster controls the release of hormones, such as melatonin, which rise in darkness and fall with exposure to light. During bright full moons or nights filled with electronic illumination, melatonin release can be delayed, slightly shifting the onset of sleep. Studies comparing sleep patterns in rural and urban populations show that even dim lunar light continues to influence rest, a subtle inheritance from an older world that slept under open skies. The rhythm extends beyond nightfall. Fluctuations in body temperature, heart rate, and alertness all follow circadian timing, shaped by evolutionary pressures that once depended on day-night transitions. Disruptions, such as jet lag or shift work, illustrate how deeply the pattern is wired into physiology. At the molecular level, circadian genes turn on and off in feedback loops, generating self-sustaining oscillations that keep time even in total darkness. External light merely resets them each day, aligning the internal clock with the cosmic one. When science describes these cycles, it reduces them to measurable variables: wavelength, photon flux, hormone concentration. But the experience remains personal. As light fades, the brain lowers its frequency of electrical activity and breathing deepens to match. The same gravitational forces that move oceans act imperceptibly on the fluids within us, shaping a world where physics and biology overlap. Each of us is a smaller version of the Earth-Moon system, governed by motion, timing, and equilibrium. If you are listening in darkness now, you can let that knowledge work as reassurance rather than instruction. Your body already knows how to follow the pattern. It has been doing so since life first sensed the turning of the planet. The moon's light, filtered through the atmosphere, is both ancient and immediate, a reminder that cycles do not demand attention to continue. Sleep arrives when the mind joins the planet's rhythm: rotation, tide, breath, and pulse aligned. Let night be an experiment in calm. Let the moon mark the passage of thought into rest. After the moon's crust thickened and the great bombardment began to slow, heat from its interior continued to shape the surface. Although small compared with Earth, the moon retained enough radioactive elements, uranium, thorium, and potassium, to keep its mantle partially molten for hundreds of millions of years. That trapped energy eventually forced its way upward through fractures left by earlier impacts, creating the vast plains we now call maria, or seas. They are not seas of water but frozen flows of basalt, evidence that the moon once breathed fire. The process was gradual. Large asteroids striking the thin crust cracked it deeply, opening conduits to the still hot mantle below. When pressure built high enough, molten basalt rose along these channels and spread across low-lying basins. Because the moon has almost no atmosphere, the lava flowed far and fast. There was no air to cool it quickly or to carry explosive gases. Each eruption filled a depression tens or hundreds of kilometers wide, forming smooth plains that solidified into dark rock. Viewed from Earth, these regions give the moon its familiar pattern, the face humans have traced into stories for thousands of years. Chemically, lunar basalt is rich in iron and magnesium, similar to volcanic rocks on Earth but lacking in volatile elements such as water and sulfur. Its crystals of pyroxene and olivine tell geologists about temperature and cooling rate. By examining microscopic features called vesicles, scientists can determine the amount of gas once dissolved in the lava and the speed at which it escaped. Radiometric dating of samples brought back by Apollo missions shows that most mare basalts formed between 3 and 4 billion years ago, long after the crust had solidified. Some younger flows, detected by orbital instruments, may be only 1 billion years old, proof that the moon's interior cooled slowly, releasing its final heat in stages. The flows are immense. Individual sheets can be more than 1 kilometer thick, and the largest basins, Imbrium, Tranquillitatis, Serenitatis, span more than 1,000 kilometers. Underneath, the dense basalt adds extra mass that alters local gravity. Spacecraft mapping these variations discovered mascons, short for mass concentrations, regions where the stronger pull subtly bends orbits. Engineers must account for them when navigating probes around the Moon. Another example of how geology and physics remain intertwined even after billions of years. Volcanic activity also left traces of transient atmospheres. As magma erupted, it released carbon monoxide, sulfur dioxide, and sodium vapor, forming thin clouds that quickly escaped to space. Recent detectors aboard lunar orbiters have confirmed faint remnants of these gases, forming what scientists call an exosphere, a near vacuum where atoms rarely collide. In this delicate environment, each molecule can travel the entire circumference of the Moon before falling back to the surface or drifting away under solar radiation. Through remote sensing, scientists analyze subtle differences in color and reflectivity to map composition across the Maria. The variations reveal flows of differing ages, overlapping like layers of paint on stone. Instruments that measure infrared spectra detect the signatures of glassy volcanic beads, fragments of rock frozen while airborne during explosive eruptions. These discoveries expand our understanding of how planetary bodies lose internal heat, showing that even small worlds remain active far longer than once believed. To the eye, the Maria appear serene, wide and unchanging, but their stillness hides a history of pressure and release. Each dark plain was once a glowing river of rock, moving silently beneath an airless sky. The brightness contrast between highlands and Maria is not just visual. It is the record of time itself, older lightstone beside younger dark. When you look up, that pattern speaks of equilibrium achieved after fire. The Moon's face is a geological memory, a balance between violence and rest, captured in the color of basalt and the reflection of sunlight. And if you let your gaze linger, the same calm that settled over cooling lava settles over thought. Energy finds its limit, and silence takes its place. The seas of basalt may no longer flow, but their rhythm remains, the slow breathing of a world that learned how to release its heat without breaking apart. The Moon's stillness is not just visual, it is physical. It has no air to move, no wind to shape its landscape, no weather to erase its history. Every rock, every footprint, every crater remains almost exactly as it was left. The silence is not absence but consequence, an outcome of size, gravity, and proximity to the Sun. The Moon's escape velocity, the speed needed for a gas molecule to avoid being pulled back by gravity, is about 2.5 kilometers per second. That is less than 1/5 of Earth's. When the Moon was young and hot, volcanic eruptions and impacts released gases into its surroundings, but thermal motion easily exceeded this low escape speed. Light atoms such as hydrogen, helium, and oxygen drifted away into space. Solar radiation then stripped what remained, and without replenishment, the atmosphere disappeared. What endures today is an exosphere, a veil of particles so sparse that each molecule can travel hundreds of kilometers before meeting another. This absence of atmosphere has several scientific consequences. Without air, there is no aerodynamic erosion. The sharp edges of craters and rocks remain unsoftened for billions of years. No water vapor condenses, no rain or frost forms except in a few shadowed craters at the poles. There are no clouds to diffuse sunlight, so shadows fall black and distinct. The surface heats to more than 100 degrees Celsius under full sunlight and drops to below -100 at night. Such extremes create thermal stress that slowly fractures rock but never smooths it away. The result is a surface preserved in extraordinary detail, a geological time capsule of the early solar system. The absence of air also means no sound. Acoustic waves require a medium to travel through. On the Moon, vibrations remain trapped in rock and dust. Even when astronauts worked and moved, they heard only through the solid contact of their suits and visors. The stillness is not metaphorical but literal, an environment where energy cannot carry as it does on Earth. This vacuum allows telescopes placed there to observe the universe without atmospheric distortion, offering future missions an ideal platform for astronomy. In this airless world, sunlight behaves differently. Without atmospheric scattering, the sky is not blue but black, even at midday. Stars remain visible beside the brilliant sun, their light unfiltered and direct. Temperature gradients occur only where light meets shadow, producing conditions that would challenge any material. Spacecraft engineers study these transitions carefully to design instruments and habitats capable of surviving such contrasts. The lack of atmosphere also protects a valuable record: the solar wind. Streams of charged particles from the sun strike the lunar surface unimpeded, embedding atoms of helium, hydrogen, and neon into the top layer of dust. By analyzing these implanted gases, scientists reconstruct changes in solar activity over billions of years. The Moon's surface is not only ancient rock, it is an archive of solar history, storing a record of radiation and cosmic chemistry. For all its harshness, this environment has become a resource for science. Seismic instruments once placed by astronauts recorded tiny moonquakes, vibrations caused by thermal expansion and tidal flexing. The data reveal a solid crust, a partially molten mantle, and a small metallic core. Combined with gravity measurements, they provide a complete picture of a world shaped more by physics than by weather. To the human eye, this stillness can feel almost peaceful. A place without sound, air, or motion becomes a mirror for thought itself. The absence of atmosphere erases distraction. It turns the landscape into pure geometry, light, shadow, and time. When you imagine standing there, every movement slows, every echo disappears, leaving only heartbeat and breath. It is a reminder that quiet is not emptiness, but clarity, that sometimes the lack of noise reveals more than its presence. Across the Moon's pale surface lies a record of collision and endurance. Each crater, ridge, and basin is a data point in a story of cosmic bombardment that once shaped every world in the inner solar system. Unlike Earth, whose atmosphere and tectonics erase the past, the Moon keeps its scars. They accumulate quietly, preserving the history of impacts in unbroken sequence for more than 4 billion years. The study of these scars forms a branch of planetary science called impact cratering chronology. Scientists analyze crater sizes, depths, and overlap to determine their relative ages. Larger craters tend to be older because smaller impacts occur more frequently and later overlap them. By counting craters within a given area and comparing those numbers with radiometric dates from returned samples, researchers build a timeline of surface activity. The Moon thus serves as a calibration tool. Its surface density of craters provides the scale used to date the ages of other planets and moons across the solar system. An impact begins with velocity. Most asteroids and comets strike the Moon at speeds between 15 and 20 kilometers per second. At such energy, solid rock behaves like fluid. Upon impact, kinetic energy converts into shock waves that melt and vaporize material within milliseconds. A central cavity opens, rim walls rebound, and molten ejecta spreads outward. In large basins, the rebound lifts a central peak or forms concentric rings, features visible even through backyard telescopes. When the molten rock cools, it traps fragments of older crust, creating mixed breccias that geologists later analyze for composition and age. Because there is no atmosphere, incoming meteoroids, large or small, arrive unimpeded. Micrometeorites continue to fall every day, striking with enough energy to melt tiny patches of soil. Over time, these impacts grind the upper layer of the surface into a fine powder called regolith. This dusty layer averages several meters thick in older regions. Within it lie glassy beads and microscopic spherules, produced by repeated melting and quenching. Each grain carries traces of the event that formed it, making lunar soil a complex archive of microcollisions. Laboratory analysis of these particles reveals extraordinary detail. Under electron microscopes, scientists can see glass fragments fused with metallic droplets, each marking a temperature spike of more than 1,000 degrees Celsius. Radiometric dating shows that the rate of large impacts declined sharply after the first billion years, suggesting the solar system gradually cleared its orbiting debris. Still, occasional collisions continued. The youngest visible craters, such as Tycho and Copernicus, formed less than 100 million years ago, recent by geological standards. Their bright ejecta rays stand out because the surface has not yet been darkened by later micrometeorite impacts and solar radiation. The lunar cratering record provides insight beyond the Moon itself. It informs models of asteroid populations, helps estimate the probability of impacts on Earth, and calibrates the age of other planetary surfaces. For instance, counting craters on Mars or Mercury and comparing their density to lunar data allows scientists to infer their relative geologic ages even without samples. In this way, the Moon acts as a universal clock, its surface reading like a ledger written in stone. For all its precision, the record carries an emotional weight. Each crater represents a moment of extreme transformation, a second when energy reshaped matter and then froze it into permanence. The Moon's silence amplifies that contrast, motion followed by stillness, heat replaced by cold. When you look at its mottled face, you see billions of impacts turned into pattern, violence rendered into symmetry. It is the solar system's diary of change, open for anyone to read who can translate light and shadow. And in that reading, there is calm. The same laws that once sent asteroids crashing through space now keep the orbit stable. Where destruction once dominated, equilibrium endures. The Moon reminds us that memory is not always soft. Sometimes it is carved, preserved by the absence of air and time. Each crater is a silent entry in a journal that began before life existed, still legible beneath tonight's quiet light. If you stood on the Moon and looked back toward Earth, the sight would fill the sky. Our planet would appear 14 times larger than the Moon appears to us, its colors alive against the black background of space, deep oceans, white clouds, green continents turning slowly through light and shadow. This view, known as Earthshine, connects two worlds through light, geometry, and shared history. The science of this reflection begins with the physics of illumination. Sunlight strikes Earth, and a portion of it reflects toward the Moon. Because Earth's surface and atmosphere scatter light efficiently, especially from clouds and oceans, it acts as a vast mirror. When this reflected light reaches the Moon, it illuminates its darkened portion, making the faint outline visible to observers on Earth during the crescent phase. Astronomers use sensitive photometers to measure the intensity of this glow, calculating how much sunlight Earth reflects, its albedo. The value averages about 30%, meaning nearly a third of incoming sunlight is scattered back into space. Changes in cloud cover, ice extent, or vegetation subtly alter this reflection, allowing scientists to monitor climate variations from afar. From the Moon's surface, Earth does not rise and set as the Moon does here. Because of tidal locking, one lunar hemisphere always faces Earth, and from that hemisphere our planet hangs motionless in the sky. It waxes and wanes through its own phases, full Earth when we see a new moon, new Earth when we see a full moon. To an astronaut standing near the lunar equator, Earth would cast enough light to read by, its brilliance more than 100 times greater than moonlight on our world. That constant presence would mark time differently, day and night defined not by the sun's motion, but by the slow rotation of shadows across an unmoving Earth. Scientists study Earthshine to learn about both bodies. By comparing the reflected spectra of sunlight from Earth and Moon, researchers can infer details about atmospheric composition, cloud height, and even the potential habitability of exoplanets that resemble our own. When telescopes detect similar signatures, oxygen absorption lines, water vapor, or chlorophyll-like reflections in distant worlds, the method traces directly back to these measurements of our reflection on the Moon. In this way, the Earth-Moon system becomes a natural laboratory for planetary science. Earth also influences the Moon through light beyond the visible spectrum. Infrared radiation emitted from our planet warms the near side of the lunar surface slightly more than the far side. This subtle difference, measurable with thermal instruments, contributes to the temperature asymmetry already established by the thicker crust on the far side. Even in stillness, energy continues to flow between the two worlds, radiative, gravitational, and magnetic exchanges linking them across space. The image of Earth from the Moon is more than a visual curiosity, it carries scientific and emotional meaning. When Apollo astronauts captured the first photographs of our planet hanging in darkness, those images reshaped human understanding. They revealed Earth not as a boundless expanse, but as a fragile sphere of atmosphere and water, finite and shared. Environmental scientists later used such perspectives to model global energy balance and climate dynamics, emphasizing how thin the protective layer of air truly is. The reflection became both a tool of measurement and a symbol of responsibility. And yet, for all the precision of data, the view remains profoundly simple. A luminous world above a silent one, each bound to the other by gravity and light. The Moon mirrors Earth's presence just as Earth mirrors the Sun's, a chain of reflection extending from star to planet to satellite. When you look at the Moon tonight, some of the light returning to your eyes has touched both worlds. It has left the Sun, glanced off oceans, crossed space, brushed the lunar surface, and found its way home again. In that journey, one can sense continuity, the unbroken dialogue between warmth and cold, motion and rest, illumination and quiet. The Moon's influence on Earth extends far beyond tides and light. Over billions of years, it has quietly shaped the conditions that allowed life to begin, adapt, and endure. Without its gravitational presence, Earth's rotation, climate, and even the rhythm of biological activity might have been profoundly different. The story of evolution is intertwined with the Moon's steady pull. The first connection is stability. Earth's axial tilt, about 23.5 degrees, creates the alternation of seasons. Computer models show that without the Moon's stabilizing effect, gravitational interactions with other planets could cause the tilt to vary chaotically, sometimes by tens of degrees. Such swings would produce extreme climatic changes, poles turning tropical, equators freezing, ecosystems collapsing and reforming on unpredictable timescales. The Moon's mass, though small compared with Earth's, acts as a gyroscope, damping these oscillations and preserving a relatively stable climate. That steadiness gave evolution the continuity it needed for complex life to develop. The second link is tides. 4 billion years ago, when the Moon was much closer, tidal forces were hundreds of times stronger. They produced vast coastal zones where shallow water alternated with dry land twice each day. These environments concentrated organic molecules, promoting chemical reactions that may have led to the first self-replicating structures. Later, such intertidal regions became ecological laboratories, home to species that gradually adapted from marine to terrestrial life. Fossil evidence suggests that many early amphibians evolved in areas where tides created temporary pools, a direct biological imprint of lunar gravity. Even today, many organisms follow lunar rhythms. Marine worms spawn during specific moon phases, coral polyps release gametes under the full moon, and certain fish coordinate migration with tidal cycles. These patterns are guided by internal biological clocks, fine-tuned to the regular intervals of lunar light and gravitational influence. Researchers studying circatidal and circalunar rhythms have found that these cycles are encoded at the genetic level, showing how deeply evolution has incorporated celestial timing into the machinery of life. The Moon may also have affected Earth's magnetic environment and atmosphere indirectly. By stabilizing rotation and slowing the planet's spin, it helped maintain a balance between core convection and surface conditions. The persistent magnetic field that shields life from solar radiation relies on the slow circulation of molten iron in Earth's core. Had rotation varied more wildly, the field might have weakened or collapsed, leaving the surface exposed to charged particles and ultraviolet radiation. Thus, the Moon's braking effect contributed indirectly to the continuity of protection that made surface life sustainable. Geologists find further evidence of the Moon's role in ancient rock layers. Rhythmic sedimentary structures called tidal rhythmites capture patterns of rising and falling sea levels over immense spans of time. By measuring the spacing of these layers, scientists can estimate how many tidal cycles occurred per month and how many days per year existed at that epoch. These rock calendars confirm both the gradual retreat of the Moon and the lengthening of Earth's day. They transform an abstract concept, gravitational interaction, into something tangible, etched in stone. From a biological perspective, the Moon's presence represents a steady metronome of environmental rhythm. Every form of life that senses day and night, wet and dry, bright and dark, is responding to the interplay between Earth's rotation and the Moon's orbit. That rhythm may have imprinted itself on neural patterns, hormonal cycles, and perhaps even on the psychological comfort we associate with nightfall. To reflect on this is to see a continuity that extends from chemistry to consciousness. The same forces that lifted tides and stabilized seasons also shaped the context in which thought could emerge. When you look at the Moon, you are seeing the quiet architect of habit and balance, a celestial influence written not just in oceans and rocks, but in the biological rhythm of every living cell. Beneath the surface calm of every ocean lies a steady rhythm, a pulse drawn by the Moon's gravity and measured in the slow rise and fall of water. These tides are more than a motion of seas. They are expressions of balance between movement and rest. In their repetition, they reflect the same physical precision that guides the orbit of the Moon and the rotation of Earth. To understand them is to glimpse how the laws of motion echo in both nature and the body. The physics of tides has been mapped in extraordinary detail. Each tide represents the interaction between gravitational pull and the centrifugal force of Earth's rotation. Water flows toward the region nearest the Moon, forming a high tide, while another bulge forms on the opposite side due to inertia. The rotation of Earth carries coastlines beneath these bulges, creating two high and two low tides every day. Solar gravity adds a secondary rhythm. When the Sun and Moon align, spring tides occur, and when they form a right angle, neap tides moderate the range. Tidal amplitude depends on coastal shape, ocean depth, and planetary geometry, an exact interplay of fluid mechanics and gravitational law. This movement does not merely stir water, it stirs life. Marine organisms have evolved to synchronize with these cycles, following circadian, circatidal, and circalunar rhythms embedded in their biology. Tiny plankton drift upward at night and sink during the day, guided by light and pressure changes linked to lunar phase. Shore crabs feed between tides, adjusting behavior even when isolated in laboratory tanks. Such precision demonstrates that life does not resist celestial timing, it absorbs it. Every cell carries an internal clock built upon cycles of chemistry that mirror the external cycles of gravity and light. For the planet itself, tides are engines of subtle change. They redistribute heat, mix nutrients, and influence ocean circulation. Tidal friction within Earth's crust dissipates energy as heat, slightly altering rotation and helping to regulate the length of day. In this way, the simple rise and fall of water connects to planetary dynamics and even to long-term climate balance. No other known world hosts tides of such scale and complexity, another signature of Earth's rare equilibrium with its satellite. When we look inward, the same principle holds. Human physiology follows oscillations that parallel the movements of the sea. Heart rate, breathing, and neural activity fluctuate in rhythmic patterns governed by internal feedback loops. The pulse of blood through vessels and the expansion of lungs echo the ebb and flow of coastal tides, both constrained by physics and tuned for efficiency. Even sleep follows waves of activity and silence, an oscillation of awareness that repeats through each night. As evening advances and the moon lifts, light softens across the surface of the ocean. The gravitational pull that moves entire seas also acts upon you, imperceptibly small yet constant. It guides the rhythm of breath, the drift of thought, and the slow settling of the body toward rest. Science can describe the mechanism, mass attracting mass, fluids finding level, but its experience belongs to feeling. You do not need to measure to sense it, you simply yield to the pattern that already exists. If you are lying awake, listening, or imagining the sound of distant water, that rhythm belongs to you as much as to the planet. Each heartbeat mirrors a wave crest. Each pause between breaths is the returning tide. As you follow that cadence, you are aligning with a universal law, the same that holds the moon in orbit. There is no urgency in it, only balance. You can let gravity do its work, drawing tension away, letting quiet rise, letting the body settle as the tide does when the wind has gone. Under that pull, the mind becomes as still as the sea beneath a full moon, at once grounded and weightless. Long before clocks or calendars, people marked time by the phases of the moon. Its changing face, new, crescent, full, waning, provided the earliest visible cycle, short enough for daily life and long enough to anchor memory. Every culture built some part of its measurement of time around that rhythm. Only later did science reveal that this human habit reflects deep physical regularity, the orbital motion of a satellite that moves in predictable resonance with Earth's rotation. The moon orbits Earth once every 27 1/3 days relative to the distant stars, a period called the sidereal month. Because Earth itself moves around the sun, the moon must travel a little farther to return to the same phase, producing a synodic month of about 29 1/2 days. This difference explains why the moon does not rise at the same hour each night. Its eastward drift across the sky, roughly 13 degrees per day, makes moonrise about 50 minutes later with each rotation of Earth. The repeating pattern of light and shadow has served as nature's most accessible calendar for tens of thousands of years. Archaeological evidence confirms this early reliance. Bone carvings and stone markings dating back to the Paleolithic era show notations that align with lunar cycles. Later, agricultural societies built entire systems of planting, harvest, and ceremony around the moon's phases. The lunisolar calendars of ancient Mesopotamia and China reconciled the lunar month with the solar year by occasionally adding an extra month, a practice still preserved in some traditional calendars today. Even the word month retains its linguistic root in moon, a trace of the link between celestial motion and human timekeeping. Astronomers later refined these ancient observations with instruments and mathematics. By measuring the moon's position relative to background stars, they established precise methods of navigation at sea. Before the invention of accurate clocks, sailors used lunar distance, the angle between the moon and a chosen star, to calculate longitude. Tables listing these distances were among the earliest standardized astronomical tools. Each measurement combined geometry and timing, transforming the changing sky into a coordinate grid. Modern science still uses the moon as a measure of time, though in subtler ways. Laser ranging experiments reveal the exact length of the lunar month and track its gradual increase as the moon recedes from Earth. This expansion, caused by tidal friction, lengthens the month by about 2 milliseconds per century. Atomic clocks on Earth record these changes, allowing scientists to calculate variations in Earth's rotation to extraordinary precision. The same gravitational system that inspired the first calendars now calibrates the most advanced timekeeping technology. Lunar cycles also intersect with biological time. Many species, especially in coastal environments, align reproduction and feeding with the timing of full or new moons. Human physiology, though less directly tied, shows subtle fluctuations in sleep and hormone patterns across the lunar month. Researchers studying melatonin and cortisol levels find consistent though faint traces of this ancient synchronization. Time measured by the moon still lingers within the human body, a quiet echo of evolutionary history. Philosophically, the moon reminds us that time is not an invention but a perception of motion. Its changing light makes abstract cycles visible. It turns orbital mechanics into something you can see with the naked eye. Each phase is both prediction and confirmation, a recurring assurance that the universe keeps order. If one watches the moon night after night, noticing its slight delay in rising, it becomes clear that time itself is the product of difference, of motion against motion, of light returning in rhythm, and when night deepens, the same motion that marks calendars and governs tides offers something more personal. To follow the moon's phases is to practice patience, to measure change without hurry, to let cycles unfold as they always have. Even as technology divides seconds into finer intervals, the human sense of time still finds calm in the slow turning of light and shadow above. It is not just the measurement of hours, but the feeling of continuity, proof that everything moves, yet returns. The moon does not control the weather, yet its gravitational and orbital effects leave subtle fingerprints on Earth's atmosphere and oceans. These influences are small compared with the sun's energy, but measurable, gentle harmonics in the complex system that governs winds, tides, and long-term climate balance. Understanding them reveals how even faint forces can shape planetary patterns when given enough time. The most direct influence arises from oceanic tides. As seawater moves rhythmically under the moon's pull, it transfers energy into the atmosphere. This interaction generates slight oscillations in air pressure known as atmospheric tides. Unlike weather systems driven by temperature differences, atmospheric tides follow predictable lunar and solar schedules, peaking twice daily. Their amplitude is small, often less than a millibar, but sensitive instruments can detect them worldwide. They subtly modulate wind speeds, cloud formation, and temperature gradients, acting as a background rhythm against which weather unfolds. The lunar cycle also contributes to ocean mixing. Strong tidal currents, particularly in shallow seas and around continental shelves, churn layers of water that would otherwise remain stratified. This vertical mixing redistributes heat, oxygen, and nutrients, influencing marine ecosystems and even regional climate. For example, models show that without tidal mixing, parts of the North Atlantic would lose much of their deep water circulation, weakening the ocean conveyor belt that moderates Europe's temperature. In this way, the moon indirectly supports climate stability through the steady mechanical stirring of the seas. Subtle links extend to the atmosphere's water cycle. Scientists have observed correlations between the lunar phase and rainfall patterns in some tropical regions. During full and new moons, when Earth, Moon, and Sun align, tides in both oceans and air slightly intensify. The resulting pressure variations can influence convection, the rising of warm, moist air that leads to cloud formation and precipitation. Though the effect is minor, statistical studies confirm a small but consistent increase in rainfall during these alignments. Such findings illustrate how celestial geometry can ripple through layers of fluid and vapor until it touches weather itself. Another influence arises from the moon's long-term gravitational effect on Earth's axial precession and orbital stability. By moderating the tilt of Earth's axis, the moon helps maintain relatively consistent seasons. Without this stabilizing torque, Earth's obliquity could vary chaotically, leading to rapid transitions between ice ages and tropical epochs. Instead, the planet experiences slow, predictable cycles that stretch across tens of thousands of years, patterns known as Milankovitch cycles. These variations in tilt, orbit, shape, and axial wobble drive the pacing of glacial and interglacial ages. The Moon, by anchoring Earth's axis, ensures that these climatic rhythms evolve gradually rather than erratically, giving ecosystems time to adapt. Even light from the Moon may influence climate, though indirectly. Reflected sunlight, moonlight, is far weaker than direct solar radiation, yet it contributes to nocturnal energy balance. Its faint glow affects how much infrared heat escapes from land and water surfaces after sunset. Satellite data suggest that during bright full moons, the combined Earth-Moon albedo slightly increases the total energy reflected into space. While the effect is minimal, it underscores the interconnectedness of illumination and temperature, even across cosmic distances. All these processes operate quietly, without human notice. They are the mathematics of steadiness, the smallest adjustments that keep larger systems from drifting. The Moon's influence does not bring storms or still the winds, but it provides rhythm where chaos might otherwise reign. Every wave, every seasonal shift, carries a trace of its motion. To recognize that is to see climate not as a separate domain of weather, but as an orchestra of repeating gravitational themes. At night, when the air cools and the moon rises, those vast interactions continue unseen. Tides move, winds adjust, and heat escapes, according to rules written before life began. The same precision that governs planetary motion governs the temperature of the breeze against your skin. You can rest knowing that the calm you feel in darkness mirrors the equilibrium of a system balanced across space, the quiet assurance that the universe keeps its rhythm and that you are moving within it. Before telescopes, before mathematics described gravity, the Moon was already a constant companion in the human story. It governed calendars, inspired myth, and served as the first moving map in the night sky. Long before science measured its orbit, people had built entire systems of meaning around its changing light. The Moon connected survival to wonder, agriculture to art, and timekeeping to faith. Archaeological evidence shows that Paleolithic communities noticed its phases tens of thousands of years ago. Bone fragments engraved with parallel markings, discovered in Europe and Africa, align with the 29-day cycle of waxing and waning light. For early humans, that pattern was more than curiosity. It offered prediction. By watching the Moon, they could anticipate tides, migrations, and the passing of seasons. The first calendars were not built of gears or equations, but of light reflected across water and stone. As civilizations grew, the Moon became a celestial clock woven into ritual. Ancient Mesopotamians tracked its phases to schedule planting and harvest. In China, astronomers of the Zhou dynasty used it to refine the lunisolar calendar that still guides festivals today. The Greeks measured its motion with geometry, discovering its changing distance through the curvature of Earth's shadow during eclipses. For them, the Moon was both divine and measurable, proof that the heavens followed order, not whim. Each culture balanced reverence with observation, blending myth and mathematics in a single gesture of curiosity. Language itself preserves this history. The root of the English word month comes from mona, the Old English for moon. Similar roots appear in Sanskrit, Latin, and many indigenous languages, showing how universal the connection once was. Across continents, the Moon marked fertility, renewal, and change. Its phases mirrored cycles of growth and decay observed in the natural world. For millennia, its motion defined the rhythm of human life as surely as sunrise and sunset. The scientific revolution transformed the Moon from symbol to subject. When Galileo turned his telescope toward it in 1610, he saw mountains, shadows, and craters, proof that it was a world, not a perfect celestial sphere. Later, Newton's law of universal gravitation explained its orbit, uniting the pull that kept the moon in motion with the force that made apples fall to Earth. By linking observation to theory, humanity's relationship with the moon shifted from mythic to empirical, yet never lost its fascination. Even as the equations grew more precise, the sense of kinship remained. In the modern era, exploration replaced speculation. Robotic probes mapped its surface. Astronauts set foot upon its plains. From the perspective of space, Earth and Moon appeared together for the first time, two worlds bound by motion and light. That image, captured by orbiting spacecraft, became an emblem of unity and fragility. The Moon, once a distant light of superstition, became a mirror for understanding ourselves. Its grey plains and silent craters told us that the universe is both vast and reachable. Despite our progress, the moon continues to influence imagination. Poets still borrow its light. Musicians still time melodies to its rise. Its presence lends rhythm to storytelling, romance, and reflection. Even when science explains every crater, the feeling of mystery remains. The moon bridges logic and emotion, reminding us that comprehension and wonder are not opposites but partners in curiosity. Tonight, when its light touches your surroundings, you are part of the same lineage. The photons illuminating the ground beneath you began at the sun, traveled across space, and found their way home through reflection. That glow carries both data and dream, evidence of orbital geometry and of every human gaze that once followed it upward. In that shared light, imagination and understanding coexist, and the distance between the ancient observer and the modern scientist disappears. Every so often, the geometry between Sun, Earth, and Moon aligns with remarkable precision. When Earth passes directly between the Sun and its satellite, our planet's shadow stretches outward through space and glides across the lunar surface. To anyone watching from below, the bright disk of the full moon slowly darkens, turning copper red before returning to silver. This event, a lunar eclipse, is both predictable and profound, the visible signature of celestial motion written in shadow. The science begins with orbital mechanics. The moon's orbit is tilted about 5 degrees relative to Earth's path around the sun. Because of that small inclination, most months the moon passes slightly above or below the line of Earth's shadow, and no eclipse occurs. Only when the moon crosses that plane near the time of a full phase does alignment become exact. At such moments, sunlight that would otherwise reach the lunar surface is blocked by Earth, except for a faint rim of light refracted through our atmosphere. That refracted light filters out shorter blue wavelengths and lets longer red and orange ones pass, bathing the moon in the dim color of sunset from all around the planet. Astronomers divide the event into stages: penumbral, partial, and total. During the penumbral phase, the moon enters the lighter outer shadow, where sunlight is only partly obscured. Brightness fades subtly, often unnoticed by casual observers. As the moon moves deeper, the umbra, the dark central cone of shadow, covers its surface, and the transformation becomes dramatic. Temperatures on the moon plunge by more than 100 degrees Celsius as direct sunlight vanishes, a rapid thermal shift measurable by orbiting probes. When the moon emerges again, the light returns exactly as before, demonstrating the precision of orbital timing. For scientists, eclipses are opportunities for measurement. By timing the exact moments when the moon enters and exits Earth's shadow, astronomers refine calculations of its orbit and distance. Infrared sensors track how quickly the surface cools and reheats, revealing the thermal properties of lunar soil. Spectrographs analyzing the faint red glow provide information about Earth's atmosphere, since that light has passed through it before reaching the moon. Changes in color intensity can even hint at volcanic aerosols or dust levels in our own skies. In this way, each eclipse becomes a mirror experiment, linking two worlds. The phenomenon also offers perspective. If you were standing on the moon during a total lunar eclipse, you would see a solar eclipse of Earth, the sun hidden behind a dark planet, surrounded by a thin ring of red light. Every sunrise and sunset on Earth happening at once. That glow would be the only illumination across the lunar landscape. It reminds us that an eclipse is not darkness but geometry, the brief alignment of three moving bodies bound by gravity. Through history, eclipses inspired awe and prediction alike. Ancient astronomers in Babylon recorded them on clay tablets, discovering the Saros cycle, a repeating pattern of approximately 18 years between similar eclipses. Greek philosophers used eclipse observations to estimate the size of Earth's shadow and, from that, the moon's distance. In modern times, careful observation has verified the gradual slowing of Earth's rotation and the corresponding outward drift of the moon. Each repetition adds precision to the long story of orbital change. Yet beyond measurement lies quiet wonder. During totality, when the moon glows red and the stars brighten, time seems to slow. The same light that paints sunsets filters through our atmosphere and touches another world. In that reflection we see not mystery but continuity, proof that motion and alignment can produce beauty without intention. When the shadow passes and the light returns, the rhythm of the universe resumes as if nothing had paused. You can watch, breathe, and sense that rhythm continuing, steady as a heartbeat shared between worlds. There are moments when the moon's position in space allows it to hide the sun entirely from view. In those brief minutes, daylight collapses into twilight, temperature drops, and shadows sharpen with eerie precision. Birds grow silent, winds pause, and the horizon glows like the edge of another world. This event, a solar eclipse, is among the most striking coincidences in celestial geometry, where the apparent sizes of sun and moon in Earth's sky match almost perfectly. The coincidence exists because of distance and scale. The sun is 400 times wider than the moon, but also about 400 times farther away. The ratio produces nearly equal angular diameters, allowing the moon, though small, to cover the sun completely when their orbits align. Because the moon's orbit is slightly elliptical, its apparent size changes through the month. When it passes directly between Earth and the sun while near its closest point, a total solar eclipse occurs. When it is farther away, leaving a thin ring of sunlight visible, the event is annular, a ring of fire around a dark disk. During a total eclipse, the moon's shadow sweeps across Earth's surface at speeds of several thousand kilometers per hour. Observers along the central path experience totality, while those outside see only partial coverage. Within the narrow corridor of full shadow, day becomes night. The sun's outer atmosphere, the corona, becomes visible as a pale, ghost-like halo extending millions of kilometers into space. This rare opportunity allows scientists to study the corona's structure, temperature, and magnetic fields, phenomena usually hidden by the sun's brilliance. Eclipses have advanced science in unexpected ways. In 1819, astronomers used a solar eclipse to confirm that the moon had no significant atmosphere. Stars became visible immediately as the sun vanished. Later, in 1919, another eclipse provided one of the first tests of Einstein's general theory of relativity. Photographs taken during totality showed that starlight passing near the sun was slightly deflected, exactly as predicted by the curvature of space-time. The moon, in covering the sun, revealed the bending of the universe itself. Even partial eclipses teach physics. The sharpness of the lunar shadow, the patterns of Bailey's beads, and the diamond ring effect demonstrate how sunlight filters through valleys and peaks along the moon's edge. Observers use these patterns to refine maps of the lunar limb and improve orbital calculations. Solar physicists analyze changes in ionospheric conditions during eclipses to understand how sudden darkness affects Earth's upper atmosphere. Each event is not only spectacle but experiment, a test of precision repeated with every alignment. Culturally, eclipses once stirred fear and awe. To ancient eyes, the disappearance of the sun seemed an omen or divine act. Civilizations from China to the Americas recorded eclipses as turning points in history. Yet even early astronomers learned to predict them, transforming fear into knowledge. The same Saros cycle that governs lunar eclipses, about 18 years, applies here as well, ensuring that every pattern of shadow repeats somewhere on Earth in a rhythm older than writing. To witness totality is to feel both insignificance and connection. The sun's light, normally constant, becomes fragile. The world cools as if the planet itself takes a breath. People who experience it often describe an instinctive stillness, a pause where thought gives way to awe. Science explains the geometry, but sensation explains the meaning. The alignment ends, light floods back, and everything resumes, yet awareness lingers. It is the reminder that even certainty, like the sun, can be briefly eclipsed and then restored. When the next shadow crosses Earth, it will trace the same geometry that has existed since the moon first settled into orbit. To watch it is to participate in that continuity, to see gravity and light perform their simplest equation. As the darkness passes and warmth returns, you can sense the precision beneath beauty, motion measured so perfectly that even silence has timing. Through every month and every night, the moon returns as a silent regulator of rhythm. It pulls the oceans, guides the tides, and marks the passage of days, not only in the environment but within living bodies. Among the many patterns that connect life to the cosmos, few are as intimate as the rhythm of sleep. While circadian cycles follow the sun, subtler patterns still answer to the changing moon. Modern studies have begun to uncover how lunar light influences rest. Researchers measuring brain activity across the lunar month found that people tend to fall asleep slightly later and sleep more lightly during the full moon. Melatonin, the hormone that promotes drowsiness, shows a temporary decrease at that time, even in controlled laboratory conditions where moonlight cannot reach the eyes. This suggests an inherited sensitivity, a remnant of evolutionary adaptation when humans and their ancestors lived under open skies. The difference is small, about 20 minutes of delay, but consistent, enough to show that the body still remembers a cycle written long before artificial light. Other studies trace similar responses in non-human life. Birds adjust their nocturnal song intensity with the brightness of the moon. Fish and corals time reproduction to lunar phases. Predators and prey alter activity to take advantage of illumination or concealment. These changes reveal a simple truth. Light, even faint and reflected, carries information. It shapes behavior not through command but through pattern, reminding biology when to act and when to rest. The moon's effect on sleep is not limited to brightness. Its gravitational influence, while subtle on the scale of individuals, modulates environmental cues that structure human routine. Tides shape coastal humidity, air pressure, and even the scent of the sea. Communities built near water, where civilization first flourished, evolved habits that synchronized with these lunar intervals. Long after cities replaced shorelines, those rhythms continued inward, folded into physiology. What began as adaptation to tides became the quiet metronome of rest. Sleep itself unfolds in waves, alternating between light and deep stages. Electrical recordings from the brain show oscillations, slow, rolling patterns that repeat roughly every 90 minutes. Each cycle mirrors the larger principle of periodicity found throughout nature. Just as the moon alternates between light and dark, the mind alternates between wakefulness and dream. Neuroscientists describe this as the brain's way of conserving energy and reorganizing memory, but the underlying geometry remains the same, motion balanced by pause. For most of history, night was the domain of reflection. People slept in intervals, waking briefly before dawn to pray, write, or watch the sky. The bright phases of the moon often accompanied these moments, providing enough light to see without flame. Even now, when darkness is a choice rather than a condition, the instinct lingers. On clear nights, sleep feels lighter, dreams more vivid, as if the mind is aware of the faint pull above. Science measures sleep in minutes, hormones, and wavelengths, but experience measures it in calm. The act of resting is the body's oldest response to the universe, a cycle of surrender and renewal that echoes planetary motion. When light fades and the moon begins its slow climb, your own rhythms align with forces far beyond awareness. The same gravitational balance that moves oceans supports the pulse in your chest. The same reflection that brightens the night reminds cells when to recover. You do not command sleep, you join it. So as you lie still, let the rhythm of the moon steady your breathing. Imagine the world turning gently, the tides rising and falling without haste. Sleep is not an interruption of life, but its continuation in quieter form. The moon watches, not as symbol or mystery, but as a clock of nature, a reminder that rest, like orbit, is simply motion at peace. The connection between Earth and Moon is not static. With every tide, a trace of energy passes from one world to the other, and that slow exchange alters their distance. Laser measurements, precise to the millimeter, show that the Moon recedes from Earth by about 4 centimeters each year. It is an almost imperceptible drift, yet over millions of years it reshapes the dynamics of the entire system, a quiet unfolding written in gravity and time. The cause lies in tidal friction. As the Moon pulls on Earth's oceans, it raises bulges that move slightly ahead of the line connecting the two bodies because Earth rotates faster than the Moon orbits. This offset exerts a gravitational torque, transferring angular momentum outward. The result, Earth's rotation gradually slows and the Moon's orbit expands. Our day lengthens by roughly 2 milliseconds per century, a rate verified by comparing ancient eclipse records with modern atomic clocks. What feels eternal, the 24-hour day, is in fact a moving target. The long-term evolution of this process can be modeled with celestial mechanics. Calculations show that in about 600 million years, total solar eclipses will no longer occur. By then, the Moon will have drifted far enough that its apparent diameter in the sky will be smaller than the Sun's, producing only annular eclipses, a thin ring of light where total darkness once fell. Farther into the future, perhaps tens of billions of years ahead, Earth and Moon could reach a state of mutual tidal lock, where one hemisphere of Earth always faces the Moon and the lunar orbit stabilizes at greater distance. By that time, the Sun itself will have changed, expanding into a red giant, making such projections more poetic than practical. Still, the mathematics describes the direction clearly: outward, slower, quieter. Geological records confirm that this drift has been happening for eons. Ancient tidal rhythmites, sedimentary layers deposited by rhythmic tides, show that hundreds of millions of years ago Earth's day lasted only about 22 hours, and the Moon was closer. Each laminar pair in those rocks captures one high tide and one low, a record of gravitational dialogue preserved in stone. From these patterns, scientists reconstruct the pace of lunar recession and test the accuracy of physical models that connect past to present. The changing distance influences not only eclipses but also tides, climate, and rotational stability. As the Moon moves outward, tidal forces weaken, and Earth's rotation slows further. Future days will be longer. Tides will rise less dramatically. The axial tilt may drift slightly as the stabilizing torque diminishes, introducing subtle variations in seasonality. Yet these processes unfold so gradually that life will adapt without awareness. The pace of celestial change remains slower than the evolution of species. Astronomers use the recession rate to refine models of Earth's internal structure as well. Tidal friction depends on how energy dissipates in the oceans and mantle. By comparing observed recession with theoretical predictions, Geophysicists estimate the viscosity of the mantle and the distribution of ocean basins through time. The moon thus becomes an instrument, a natural probe revealing the physics of the planet it orbits. To imagine this drift is to grasp the scale of patience in the universe. Every ripple of the tide, every ocean current, contributes infinitesimally to a movement that only measurement can reveal. The moon we see tonight is not where it was when life began, nor where it will be when our descendants look upward in ages to come. It moves outward in silence, maintaining the same rhythm that first lifted waves along the shores of a molten Earth. If you step outside on a calm evening, that knowledge does not disturb the quiet, it deepens it. The light above travels a little farther each year, yet it still finds your eyes. The connection remains, stretched but unbroken, proof that distance can increase without separation. In gravity, as in memory, closeness is not measured in space but in influence. The moon drifts away, but its pull endures, marking time for a world that continues to turn beneath it. Light from the moon is ancient sunlight, reflected, softened, and delayed by a journey of almost 1.5 seconds. It carries no heat of its own, yet it shapes the rhythms of life and sleep through brightness and timing. For as long as humans have watched the sky, this faint glow has guided migration, night work, and rest. Even in an age of electricity, the biological clock still notices when the moon is full. Physiologists studying circadian entrainment find that light intensity as low as a few lux can influence the body's hormonal cycles. Moonlight, though 1,000 times dimmer than daylight, can suppress melatonin when exposure is prolonged. It also alters core body temperature slightly, an effect measurable in carefully controlled sleep laboratories. Participants exposed to simulated full moon levels of light take longer to fall asleep and show reduced deep sleep stages, while the opposite occurs during the darker new moon nights. These results reveal that evolution tuned the human nervous system not only to the sun's 24-hour rhythm but to the moon's 29-day modulation layered upon it. In the natural world, this sensitivity defines entire ecosystems. Coral reefs in the Pacific synchronize mass spawning with the first full moon after seasonal transitions, timing genetic exchange to tides and light. Predatory fish hunt more actively when moonlight brightens shallow waters, while plankton descend to safer depths. Owls and nightjars adjust hunting ranges. Insects calibrate navigation using the polarization of moonlight. Each behavior, observed and quantified, demonstrates how reflection and gravity together govern nocturnal life. To the scientist, these are datasets and wavelengths. To the observer at night, they are choreography written in light. Dream researchers have explored whether lunar phase influences dream vividness or recall. Though results vary, patterns appear. People report more detailed dreams near the full moon and fewer during darker nights. Electroencephalogram studies show heightened activity in brain regions associated with imagery and emotion when moonlight is stronger. The mechanism remains debated, perhaps hormonal, perhaps psychological, but it points to an enduring connection between external cycles and inner narrative. The moon, indifferent yet consistent, may still pace the theatre of the mind. Beyond physiology, the reflection itself carries lessons about perception. The moon seems luminous, yet it reflects only about 12% of the sunlight that reaches it. Its brightness is an illusion of contrast against darkness. The same physics defines how the human eye adapts at night. Rod cells amplify faint photons, reshaping them into grayscale images that feel almost blue. In that adjustment lies the bridge between astronomy and biology. Light leaving the sun, crossing space, bouncing from rock, entering the cornea, and triggering a chemical signal that becomes awareness. Dream and vision share the same photon trail. When you prepare to sleep, your body follows a choreography guided by that light. Melatonin rises, heart rate falls, breathing slows. Each cycle mirrors the waning of illumination outside. If you let attention settle on the quiet glow beyond your window, you may feel the synchronization, an ancient coordination between orbital mechanics and biology. There is no command to sleep, only a gradual invitation written into physiology. So as the night deepens, imagine the moon's pale reflection spreading across oceans and rooftops, touching every open surface with equal calm. You share that light with forests, deserts, and distant waves. Let your eyes close, not to escape the world, but to align with it. Dreams that follow are part of the same continuum. Energy from the sun transformed by the moon, translated into rest. In that cycle, you are both observer and participant, breathing in rhythm with the turning of worlds. The moon is more than a companion in the sky. It is the nearest natural laboratory for studying the solar system. Because it lacks atmosphere, weather, and life, its surface preserves a record of cosmic history in nearly pristine form. Each crater, grain of dust, and layer of rock is an unedited archive of events that shape not only the moon but also Earth. Scientists treat it as a time capsule, a place where the past remains visible and measurable. The Apollo missions revealed that lunar soil, or regolith, is a mixture of crushed rock, glass beads, and metallic particles created by continuous bombardment from micrometeorites. Without wind or water to erase them, impact features accumulate and remain stable for billions of years. By analyzing radioactive isotopes within the samples, researchers determine ages of ancient lava flows and the timeline of heavy bombardment that ended about 3.8 billion years ago. This chronology anchors the dating of planetary surfaces throughout the solar system. What we know about the age of Mars's plains or Mercury's basins comes, in part, from calibrations first derived on the Moon. Because the lunar surface lacks atmosphere, it also serves as a perfect platform for physics and astronomy experiments. Reflectors placed by Apollo astronauts continue to bounce laser pulses from Earth, allowing distance measurements accurate to a few millimeters. These data refine models of gravitational interaction and test aspects of general relativity. For example, whether the gravitational constant changes over time. So far, it does not. The measurements confirm stability to remarkable precision. Other instruments have monitored the Moon's slight internal vibrations, mapping a small metallic core and confirming that it cools steadily as heat escapes into space. The Moon's slow rotation and airless environment make it ideal for future observatories. Radio telescopes placed on its far side would be shielded from Earth's electromagnetic noise, providing access to low-frequency signals from the early universe. Infrared arrays near the poles, kept cold by permanent shadow, could study the faint light of distant galaxies. Even the dust, once a nuisance to astronauts, is a source of knowledge. Its charged grains cling to surfaces and rise slightly at lunar dawn and dusk, forming an electrostatic haze. Studying this phenomenon helps engineers design instruments for other airless worlds. Geologists use lunar samples to understand planetary differentiation, the process by which a molten body separates into crust, mantle, and core. The isotopic similarity between lunar and terrestrial rocks remains one of the strongest clues supporting the giant impact hypothesis. The theory that the Moon formed from debris after a collision between early Earth and a Mars-sized body. Every chemical signature confirms a shared origin. Thus, studying the Moon is effectively studying Earth's own beginnings under a different light. Future missions aim to use the Moon as a staging ground for deeper exploration. Its weak gravity well makes it an efficient base for launching probes toward Mars or the outer planets. Robotic drills will soon extract ice from permanently shadowed craters at the poles, providing both drinking water and hydrogen fuel. Astronomers envision laboratories powered by sunlight, reflected from mirrors on surrounding peaks, quiet places where instruments could operate for decades without interference. Each project transforms the Moon from subject of study into partner in discovery. To look at the moon through this lens is to see it not as barren but as potential. It is a landscape where questions can be asked with clarity: how planets form, how gravity behaves, how life might emerge elsewhere. In its silence lies the ideal scientific environment: stable, predictable, and unhurried. If one could stand there at night, watching Earth rise above the horizon, the view would contain both laboratory and home, experiment and observer. And perhaps that is the essence of science itself: to study the familiar from a distance until understanding brings us closer again. Half a century after the last astronaut left the moon's surface, humanity is preparing to return. This renewed effort, driven by advances in engineering, robotics, and international collaboration, reflects both curiosity and necessity. The moon has become a testing ground once again, a place to refine technologies that may one day carry humans deeper into the solar system. The return is not only a repetition of history but a continuation of exploration through new eyes and new tools. The Artemis program, led by NASA with contributions from Europe, Japan, and other partners, aims to establish a sustained presence near the lunar South Pole. Unlike the equatorial sites of the Apollo missions, these polar regions hold permanently shadowed craters where temperatures remain below -200 degrees Celsius. Orbiters equipped with spectrometers have detected hydrogen signatures there, evidence of water ice mixed with the soil. This discovery changes the practical meaning of the moon. Ice can be converted into oxygen for breathing, hydrogen for fuel, and water for life. Each molecule becomes part of a future closed-loop system that could support crews for months rather than days. To reach that future, engineers are developing spacecraft designed for reuse and endurance. The Space Launch System will carry heavy payloads beyond low Earth orbit, while the Orion capsule provides long-duration support for astronauts. A small station, the Lunar Gateway, will orbit the moon as a hub for transfer and research, allowing flexible missions to the surface. Robotic landers are already mapping terrain, testing landing systems, and gathering data on dust behavior, radiation exposure, and thermal conditions. Together, these efforts form the infrastructure for a scientific frontier that will outlast a single generation. The return also invites international participation and private innovation. Agencies and companies from multiple nations are designing landers, rovers, and habitats, each contributing pieces to a shared endeavor. This distributed approach mirrors how science itself evolves: cooperative, iterative, and global. Experiments planned for early missions include studying plant growth in lunar soil simulants, monitoring cosmic radiation, and testing three-dimensional printing using local regolith as construction material. The goal is to learn how to live off the land of another world. Beyond engineering, the new lunar exploration renews philosophical questions. What does it mean to live beyond Earth, even temporarily? How does perspective change when Earth becomes a small blue sphere again, rising above a horizon of silence? For astronauts, that view once transformed national competition into planetary awareness. For scientists and citizens alike, the moon remains a mirror reflecting both our technological reach and our capacity for reflection. The act of returning is a scientific expedition, but also an introspective one. The moon offers stability and predictability, a platform from which to build the next steps outward. Its low gravity, about 1/6 that of Earth, allows spacecraft to launch with minimal fuel. Its proximity enables rapid communication and rescue if needed. By mastering operations there, humanity rehearses for Mars and beyond. Each landing, each experiment, is part of a continuum that began when early humans first looked upward and wondered what that glowing sphere might be. Yet amid plans and programs, the essence remains unchanged. The moon does not demand attention, it simply waits, patient as always. Every rocket launch, every line of code, every dream of exploration moves within the same gravitational conversation that has existed since the beginning. When humans set foot there again, They will stand not as conquerors but as participants in that ongoing dialogue between curiosity and creation. The footprints will fade slowly, as they did before, but the purpose behind them will endure, a testament to both ambition and humility under the same quiet light. Science describes the moon through equations of gravity, orbit, and reflection. Art describes it through memory, emotion, and light. Across civilizations, the same object has been both a clock of the heavens and a canvas for imagination. The dialogue between observation and meaning has lasted as long as human thought itself. In ancient cultures, the moon was not merely a light in the sky but a symbol of renewal. Its phases mirrored the cycles of birth, growth, and decay seen in nature. Egyptians linked it to Thoth, the recorder of time and wisdom. Mesopotamians honored Sin, whose nightly travel measured order in the cosmos. In China, poets wrote of reunion during the Mid-Autumn Festival when families gathered under its glow. For the Maya, the moon goddess Ixchel ruled fertility and medicine, her phases guiding agricultural rituals. Across these traditions, observation blended seamlessly with metaphor. What changed in the sky reflected what changed on Earth. As knowledge expanded, artistic portrayals shifted from divine portrait to natural landscape. Renaissance painters, inspired by early telescopes, began depicting craters and shadows with astonishing accuracy. In 1691, Giovanni Cassini's maps of the lunar surface influenced both astronomy and art, showing that science could reveal beauty rather than diminish it. Later, Romantic poets, Shelley, Byron, and Wordsworth, used the moon as shorthand for solitude and reflection, translating physical distance into emotional depth. Each artistic era reinvented the moon while keeping its essence, constancy through change. Photography and film carried that symbolism into the modern world. When Georges Méliès released A Trip to the Moon in 1902, he captured both wonder and irony, imagining a rocket striking the lunar face. Decades later, real spacecraft fulfilled that dream, and artists responded again, composers writing symphonies of silence, filmmakers framing astronauts against stark horizons, poets describing the sound of footsteps in dust older than life. The moon became a mirror for modern ambition and the humility that follows achievement. Cultural psychologists note that lunar imagery recurs in languages of emotion. Phrases like moonstruck, lunacy, or under the same moon reveal how deeply its presence permeates thought. While the term lunatic once reflected superstition about lunar influence, contemporary studies have largely disproven direct behavioral effects. Still, the association persists, reminding us that meaning endures even after myths are revised. In literature and music, the moon remains a symbol of longing, distant yet familiar, reachable yet untouchable. Artists today continue to use the moon as both subject and collaborator. Installations recreate its surface with light projections. Musicians compose works timed to its phases. Photographers capture its rise over urban skylines as a measure of scale between nature and technology. Even in digital art, where every pixel can be invented, the moon's image carries authenticity, evidence that the universe still provides its own design. The interplay between science and art around the moon forms a complete circle. Science explains how light reflects from basaltic plains and why shadows appear blue-gray. Art turns that explanation into experience. Neither discipline diminishes the other. To the physicist, the moon teaches about albedo and gravitational resonance. To the painter, it teaches about restraint and contrast. Both seek clarity, one through measurement, the other through meaning. And beneath these interpretations lies the same human impulse: to find connection through observation. When you look at the moon tonight, you join every person who has ever looked before you, scientist, poet, or child. It is the one gallery that has never closed, the exhibition that spans continents and centuries. Whether studied through a telescope or painted from memory, The moon offers the same lesson. The closer you look, the more you realize you are part of what you see. If you could look at Earth and Moon from far away, their connection would appear effortless. A planet and its satellite turning together through space, bound by gravity yet moving in freedom. Their relationship is not static but dynamic, a dialogue of motion, energy, and time. Everything we have learned, from tides to eclipses, from ancient calendars to modern missions, unfolds from that single gravitational thread. The moon's orbit is both a consequence and a cause. It formed from collision, shaped by rotation, and refined by friction. Each equation that describes its path also describes stability, the way momentum balances force, the way the pull of gravity curves space into predictable motion. Because of this precision, our planet's tilt remains steady, our seasons follow order, and life endures within a range of calm that allows oceans, air, and thought to exist. The moon's steadying presence, invisible in daily life, is one of the quiet reasons Earth remains hospitable. That balance reaches beyond mechanics. The moon links every domain of science, geology, biology, climatology, astronomy, by showing how interconnected systems behave across scales. The same tidal forces that move entire seas also influence molecules in living cells. The same cycles that time eclipses guide the growth of coral and the rest of human sleep. Through the moon we recognize pattern as a universal law, motion alternating with rest, energy yielding to rhythm. It teaches that stability is not stillness but harmony among moving parts. Even the small details of its light carry meaning. The moon shines not by its own power but by reflection, scattering sunlight in all directions. Every photon that reaches your eyes tonight has touched both worlds, leaving the sun, brushing lunar dust, then crossing space to arrive here. That simple journey connects cosmic physics with personal experience. To study the moon is to study light itself, how it travels, interacts, and transforms into awareness. The scientific story continues. Future explorers will map craters more precisely, analyze ice in shadowed valleys, and test instruments that will one day work on Mars. The moon remains our most accessible proving ground, a place where questions meet evidence without the interference of air or weather. Every measurement adds to a body of knowledge that began when ancient observers watched its changing shape and wondered what governed its rhythm. The wonder persists, even when the mathematics are known. Yet knowledge alone does not complete the picture. To look up is also to feel continuity, the understanding that what moves in the heavens moves within us. Our own bodies, built from the same elements forged in stars, respond to gravity, light, and time just as the oceans do. The pulse you feel, the breath you take, the drift toward rest, all belong to the same fabric of motion that binds planet and moon. Science explains the process. Experience gives it meaning. So as the night deepens and light softens, let the certainty of that bond bring calm. You are part of a system older than memory and wider than imagination. The moon rises not to command sleep, but to remind you that rest is also orbit, a return to balance, a pause in motion that keeps everything aligned. Let thought slow as Earth itself turns beneath a silent companion. Let the rhythm of breath match the quiet pull of gravity, steady and sure. And when your eyes grow heavy, remember that the same light tracing the edge of the moon touches your own world with equal precision. Its reflection carries the story of origin and the promise of return. In that knowledge, the universe feels close, measured not in distance but in understanding. We from Sleepy Stories wish you a good night.